สวัสดีครับ In this clip, we will discuss the solution of test number 5. In this test, it's about the calculation about the vector. Okay. Vector is a mathematical quantity that we often use in physics, especially when we want to describe the motion of an object, because to describe the motion of an object you have to specify both the magnitude and direction of many quantities. For example, if you want to specify the position of an object, you have to specify how far of that object from you and in what direction. Okay, and we use vector to do this job. Okay, in this problem, the question is that a radar station locates a sinking ship at length 17.3 km and bearing 136 degrees clockwise from north. From the swim station, the rescue plane is at horizontal length 19.6 km, 153 degrees clockwise from north, with elevation 2.2 km. How far apart are the plane and ship? Okay. And to solve this problem, we can use the concept of the vector. But before we go to solve this problem, let us discuss a little bit about vector. Here we will talk about some property of vector. There are a lot of property of vector that we use in physics, and when it's necessary, we will talk about that property. Here we will talk about some basic property of vector. First, what is vector? Vector is a quantity that you have to specify both direction and magnitude. Okay, direction and the magnitude of the vector. You have to specify both. Okay, we have to specify both direction and magnitude. Okay. We may say that the most basic vector is the position vector. The position vector is the vector that points from some reference point, for example yourself, to some point that you want to specify its position. Okay, so if you are a reference and you want to specify the position of an object at position P, you can use the position vector to point from you to that object. Okay, and to specify the position of P, you have to specify both the magnitude, that is the distance from you to the object at point P, and the direction from you, point from you to that object. Okay, and this is the vector. Okay. We will see later that the vector, we can use the vector to specify more than the position of the object. We can use the vector to specify the velocity of the object. We can use the vector to specify the acceleration of the object. We can use the vector to specify the force, the momentum, so on. Okay, but in the first part, that we are interested only in the kinematic of the object. The main vector that we will deal with is the position vector, velocity vector, and acceleration vector. Okay. Now, the second property of the vector is that the addition of vector. Okay. The basic, the easiest way to write down the vector is to write it graphically as an arrow, like in this figure. As in this figure, like it is an arrow point from U to the object at point P. Okay. Now, if we have two vectors, if you have a vector from one point to another point, and if I call this a vector A, and we have another vector B, B is not necessary to be near A. It can be anywhere. We have vector A and vector B like this. And we want to add these two vectors. We define that the addition of A and B will result as the new vector C. And the new vector C can be drawn by we put the vector B, the tail of the vector B, to the head of the vector A, and then we draw an arrow from the tail of A to the head of B, and we call this the vector C. So this is the addition of vectors. Okay. Next, we have that addition of vector has the property of commutation. That is, if we can write A plus B and then plus C, it will equal to A plus B plus C, which means that the order of A, B, and C are not important. We can add A and B first and then add to C, or we can add B and C first and then go add to A and give the same result. Okay, this is a basic property. I will not prove this property. You have to go to the math class to prove this property. I think you should learn this from high school already. Okay. Next, it is about the component of a vector. When we have a vector, for example, if we have a vector A and if we have a line, this dashed line, we will say that we can define a vector if we call this line C. Okay, we can define the vector AC, and we call this AC is a component of A along the line C. Okay, this AC is a vector that's drawn from the tail of vector A to the point. If we draw a line perpendicular to C like this, and this is the intersection between this line and the line C, and we draw the vector from tail of A to AC, and this is the component of A along line C. Okay, this is the definition of the component of the vector, and this definition of the component is very important, especially when we write down a vector and we also write down the left-hand axis. Okay, for example, if we write this as x-axis and y-axis, and then we define the component of vector A along x-axis and y-axis. So this is AX and this is AY. Okay, you can see that AX and AY are perpendicular to each other. Right? AX and AY are perpendicular. This. And we can also see that A is equal to AX plus AY. Okay, AX plus AY. And we can also say that the magnitude or the length of the vector A, we can write it as A, just A, or the vector A in the absolute sign, like this, is equal to AX squared plus AY squared, where square root of AX squared plus AY squared, where AX is the magnitude or the length of the vector AX and AY is the magnitude or the length of vector AY. This comes from the Pythagoras theorem. Okay, and you can see that if we have two vectors, A, which can write as AX plus AY, and B as BX plus BY. Okay. If we add A plus B, it will equal to AX plus BX plus AY plus BY. This is a commutative property that we discussed earlier. Okay. Now, the last one for this problem is the subtraction between two vectors. Okay. We say that C is equal to A minus B, mean that C is equal to A plus minus B, and minus B is a vector that has the same magnitude of B but point in the opposite direction. If we have B like this, we will have minus B, same magnitude but point opposite direction. Okay, so that's all we need now for the test number 5. Okay, so let's solve the problem. First, we will draw the left length axis. Okay, we may have this as a north, east, south, west, and the vertical axis as the altitude, the elevation or elevation. Okay. Now, if we put the radar station at the origin of this reference axis, okay, and the problem say that the radar station locate a sync ship at range 17.3 kilometer and bearing 136 degree clockwise from north. So it means that it is a pointing vector or position vector from the station to the sync ship. Okay, this specify the position vector from the station to the sync ship. So we can write this angle is 136 degree clockwise. It's a clockwise direction from north, and the distance is what? 17.3 kilometer. 17.3 kilometer. So the sync ship is here with respect to the radar station. Okay. And also, we have that there is a rescue plane. It says that it's at the elevation of 2.2 kilometer. Okay, so this is a 2.2 kilometer, and the vector, position vector point at horizontal range 19.6 kilometer and 153 degree clockwise. The horizontal range means that the range of the plane on the horizontal plane. Okay, it's easier to explain this as diagram. That is, if the plane is here and you draw the line perpendicular to the the north, east, west, south plane, or the surface, the earth surface plane, and you draw the line here. Okay, we have this angle equal to 153 degree, and the distance is 19.6 kilometer. So it's 19.6 kilometer. Now the question is that how far from the rescue plane to the sync ship? It means that we have to draw the position vector from the plane to the sync ship. Okay, and we calculate the distance or the magnitude of this position vector. Okay, this position vector R. Now, we can write down. I forget to discuss something. let's go back to the discussion on the component of the vector. Okay. If the angle between the vector A and the line C is theta, we can say that AC is equal to A cos theta. Okay, from trigonometry, we can see that the length of AC is equal to the length of A times cos theta. Okay, and when we go to this definition of the component along two perpendicular axes, okay, we can also say that if this angle is theta, we will have that AX is equal to A cos theta and AY is equal to A sin theta. Okay, again, we can use the trigonometry to prove this. It's very simple. Okay. Now, go back to this problem. You can see that if we calculate okay, I will say that this vector is a vector R1, okay, and this vector from the station to the plane is vector R2, okay. And from this figure, you can see that vector R is vector R plus vector R2 is equal to vector R1, right? If you look at this figure, this is R2, this is R, and this is R1. So R1 is equal to R plus R2, or we can say that R is equal to R1 minus R2. Okay. Now we can write vector R1 as a component of R1 along the north-south axis. Okay, plus vector R1 along the east-west axis. Okay, mean that we dissolve the vector R1 into two components along the north-south axis and east-west axis. Okay. Also, we can write the vector R2, which is R2 along the north-south axis plus R2 along the east-west axis, and then plus R2 along the altitude axis. Okay, you can see that R1 only have two components, that is along the north-south axis and east-west axis, because the kinship are on the surface. Okay, but the plane are not on the surface, are on some elevation or altitude from the ground. Okay, so we have one more addition component along the axis A. Okay, so we have these three components. Okay, then we can write that R is equal to R1 minus R2, which equal to R1 north-south axis plus R1 east-west axis plus R2 north-south axis plus R2 east-west axis plus R2 along the altitude axis. Altitude, not attitude, altitude. Okay. Again, now we can use the commutative property of the vector, which we can write this as R1 of the north-south plus R2 of the north-south plus R1 of the east-west plus R2 of the east-west plus R2 of the altitude. Okay. The way we write down this vector like this is useful because at the end we can write, for example, this R1 and R2 along the north-south axis as one component, as a vector that point along the axis, the north-south axis, and these two, this summation is another vector that point along the east-west axis, and the last one is the vector that point along the altitude axis. And those three groups of vectors are all perpendicular. So at the end we can find the magnitude from the plane to the sinking ship using the Pythagoras theorem very easily. Okay, so we have that R1 along the north-south axis is equal to R1 cos. Okay, if you look at this, it is equal to R1 cos 136 degree, right? Because this 136 degree is the angle between R1 and the north-south axis. Okay. R2, this is the component, is the magnitude, okay, is equal to R2 cos 153 degree. Okay. So we can say that the magnitude of R1 along the north-south axis plus R2 along the north-south axis is equal to R1 cos 136 degree plus R2 cos 133 degree. Okay. Okay. I change this a little bit. That is, we may not need to write down the absolute here. Okay. Why I ignore the absolute symbol? Is it because here R1 the component of R1 along the north-south axis and component of R2 along the north-south axis point along the same line. Okay, when vector point along the same line, for example, if we have the vector A and vector B like this, and we add these two vectors to be vector C, you can see that the magnitude of C is equal to the magnitude of A plus magnitude of B. Okay, so we can use the magnitude of these two vectors add together to get the magnitude of the result. And if when we add these two magnitudes and it have a positive value, it means that it points along the positive direction that we define. For example, if we define the north direction is a positive direction, and if the result of the addition of two vectors, component of two vectors along the northeast axis has a positive value, it means that it's point to the north. Okay, but if it's negative, it means that it points to the south. Okay, so we can ignore the absolute symbol here. Okay, so we have this, and also we have R1 is west is equal to R1 sine 136 degree. Okay. Because the east-west axis is perpendicular to the north-south axis. So if we go to this, you can see that AX, if X is a north-south axis and Y is a east-west axis, we have AX is equal to A cos theta and AY is equal to A sin theta. Okay, and with the same reason, we have the R1 of the east-west axis is equal to R1 sine 136 and R2 of the east-west axis is equal to R2 sine 153 degree. Okay, and R1 is west plus R2 is west is equal to R1 sine 136 degree plus R2 sine 153 degree. Okay. Oh. Okay. Let me change a little bit on this. this is quite a little bit complicated because you have to write down the vector in 3 dimensions. You will learn about how to use the unit vector along the left-hand axis, and it will simplify a lot the problem like this. Anyway, I will write down this as R2. This is a vector R2 horizontal, and this is a vector R2A. And we have vector R2 is equal to the vector R2 horizontal plus the vector R2A. Right? If you draw this vector, you can see that these two vectors are perpendicular because vector R2A point along axis A and vector R2 horizontal are on the surface, northeast, west, south surface or northeast, west, south plane with perpendicular to the attitude axis A. Okay. Now, when we write down this equation, we have that this is R2 horizontal. This is R2 horizontal, and this is R2A. Okay. So I change this is R2 horizontal, R2 horizontal, R2 horizontal, R2 horizontal, and R2A. Okay. This is R2 horizontal, R2 horizontal, R2 horizontal, and this is R2 horizontal. Also, this is R2 horizontal, R2 horizontal. Okay. And now we can write down the magnitude of the vector R. Okay. Now we have that the vector R, the magnitude of vector R is the square root of R1 is west plus R2 horizontal is no north south square plus R1 is west plus R2 horizontal is west square plus R2A square. Okay. Now let's see. Let's go back to this. We know that R1 is the magnitude of R1 is 17.3 kilometer. So if FD we have is 17.3 kilometer time cos 136, okay, plus R2 horizontal is 19.6 kilometer. Time cos 153 degree. And this result, let's use the calculator. 17.3 times cos 136 plus 19.6 times cos 153 is equal to 29 plus 0.908 minus kilometer. The minus sign say that when you add the component of the north-south component of R1 and R2 horizontal, it points along the opposite direction of the north direction. And if we define the north direction as the positive, it means that this vector points along the negative or along the south direction. Okay. Okay. Now, for the east-west component, is equal to R1. R1 is equal to 17.3 sine 136 plus 19.6 times sine 133 degree. Okay, let's use the calculator. 17.3 times sine 136 plus 19.6 times sine 153, which is equal to 20.916 kilometer. And for the last one, we know that R2A is equal to the altitude of the plane, which is 2.2 kilometer. 2.2 kilometer. So we have that R is equal to square root of the first term is minus 29.908 minus 29.908 square. You can see that the minus sign is have no effect on this calculation because we have to square the number, and if minus square is positive, okay, negative square is positive, and now plus what? 20.916 kilometer. 20.916 square square plus 2.2 square. So we have square root of 29.908 square plus 20.916 square plus 2.2 square is equal to 20.916 square root of 29.908 square plus 20.916 square plus 2.2 square. Oh, plus the result is 36.562 kilometer. 36.562 kilometer. Go to the problem. What's wrong with my calculation? Oh, this is a minus sign, right? We must have the minus sign here. The minus sign here. Okay. Which means that this have to be the minus sign, and this is the minus sign, and this is the minus sign. Okay, so it means that this have to be the minus sign. Okay, and this is have to be the minus sign. Okay, so we have to change the number. 17.3 cos 136 minus, we have minus sign here, 19.6 times cos 153 . Okay, this equal to, no, we change the number. It becomes 5.019. It means that the result point along the north direction. Okay, let's see if it's reasonable. Okay, you can see that the plane, the horizontal position of the plane is here, and horizontal position of the thing is here. So the result of the vector point from this point from the plane to the thing must point along the positive north direction. So that is reasonable. Okay. Now we have that we have negative sign here. So we have 17.3 19.3 times sine 136 minus 19.6 times sine 153 is equal to 3.3828 kilometer. Okay, and this is reasonable because if we look from the vector from the plane to the sink ship, it points along the east axis, so it should have the positive value. Okay, so we change the value here to what? 5.019. 5.019 and it is equal to 3.328. So the square root of 5.019 square plus 3.328 square plus 2.2 square is equal to 6.411. 6.411. What wrong with my calculation? Oh, I put the wrong number here. It must be 7.3, not 7.6. 7.3 means that this is 3.119. Okay. The result is 6.005 kilometer, which if we round the number, so it's become 6.31. Okay, and the answer is 3.